Okay, welcome back everybody, and thanks again for joining us here today. Our next talk is by Carl Hergenrother, as Mary just announced. And Carl is an astronomer who's done a lot of work on light curves of asteroids. He worked at the Minor Planet Center as well, which really catalogs all of the asteroids and comets that we know about in the solar system. And now Carl is working for the OSIRIS-REx project, which is an LPL mission that will be sent to one of these asteroids. So please join me in welcoming Carl, and we're going to hear a lot about OSIRIS-REx.
Well, thank you everyone for coming, and just to make sure everyone can hear the sound pretty well. And if you do have, I think I might want to move, or is it that guy? Okay, let's try that again. No feedback, so I guess it was the microphone. But we do have... really loud. Okay. If you had any trouble hearing that squelching, we do have assisted listening devices that Joshua has, just in case. So for today's talk, I mean, most of you, I'm assuming, are locals. Many of you probably know about the OSIRIS-REx mission, which is a local mission, and many of you may have even seen talks about the OSIRIS-REx mission. So I'm going to try to talk about a few little different things that maybe you haven't seen in previous talks here at LPL. First, of course, we'll just have an introduction. What exactly is OSIRIS-REx? What is this mission that LPL is a major part of? Also go into a little bit of the history of OSIRIS-REx. You know, for a lot of people, when a spacecraft flies by Pluto, it just pops out of nowhere. All of a sudden, hey, we've got a spacecraft that's going by Pluto next week. It's all over the news. What people probably don't realize is that not only was it launched a few years before, but it might have been a decade or two of planning prior to NASA even deciding that we're going to go forward and fund this mission. So I'll go into a little bit of the history and politics of getting a mission selected by NASA. And then the gist of the talk, Bennu, the asteroid that's our target. Why are we going to Bennu? What do we know about it? And kind of what do we expect to learn when we get there? So OSIRIS-REx is an asteroid sample return mission. Okay. Everyone down here are major players on the mission. The main three are the University of Arizona, NASA Goddard, and Lockheed Martin, who's building the spacecraft. We also have instruments and scientists being contributed by Arizona State, the Canadian Space Agency, the French Space Agency, Kinetics, which is a private company, MIT, and of course ULA, the United Launch Alliance, is providing the, they're building the Atlas V that we're going to be launching on. We have a lot of Arizona connections. I mean, first of all, the PI, the person who basically put the proposal together and submitted and ultimately is responsible for the success of this mission, is here at LPL. All the science will be done here. Now, there will be scientists from all over the world working on the mission, but Tucson, between 2018 and 2019, will basically be ground zero for all OSIRIS-REx scientists for science, and most of the scientists will be co-located here in town. We are also contributing one of the instruments. ASU is building another instrument, and I'll go into a little more detail on these instruments. And Kinetics might be a company that you're not really aware of. They're spread all over the country, but their headquarters is up in Tempe. And they're actually the ones who are going to be doing our space navigation. In effect, they're going to be the ones flying the spacecraft. And these are guys and girls who started at JPL. They were the same people who landed near on the asteroid Eros and did the navigation for the Pluto mission, did navigation for the Mercury mission. So they're kind of the key people now. So what does OSIRIS-REx mean? The old days of Mariner 1, 2, 3, 4, 5, 6, 7, whatever, those are done. Everybody has to have a unique name, and it's usually an acronym. Now, officially, this should be New Frontiers 3. The Pluto mission would have been New Frontiers 1, Juno's New Frontiers 2. But OSIRIS-REx is an acronym. And really, it spells out the key science interests or investigations of the mission. Origins. Where did the asteroid come from? And more importantly, where did the Earth and even life and volatiles on Earth, the organics and volatiles on Earth, come from? Spectral interpretation. we've got all these asteroids out there. we've got spectra of lots of them. We've got all these meteorites. You can see a lot of them out in the atrium there. Spectra of them too. They don't always jive. So this is one of those kind of go to an asteroid, figure out exactly what it looks like, and see if we can match this up with the meteorites in our collection and try to understand why they match or why they don't match. Resource identification. At some point, humanity is going to move out among the asteroids and planets. We're going to have to learn how to live off of what's out there. So in order to do that, we have to identify what's out there. Which are the objects that do have the kind of materials you would use for building habitats? Most importantly, which are the asteroids that have water? Water is not only good for drinking, it also produces oxygen for breathing, and it produces fuel. So water is more, will be much more valuable than gold when we're out there. Security. The Earth gets hit by asteroids all the time. Most of them are really itty-bitty things we call them meteors. But every once in a while we get hit by something big, like Chelyabinsk 2 years ago, or even the Chicxulub impactor, which wiped out most of the dinosaurs. Assuming you believe the birds are dinosaurs or not. So by going to this particular object, which by the way is actually considered the most dangerous asteroid, at least over the next 200-year time scale. That is about a 1 in 2,000 chance of hitting the Earth tail end of the 22nd century, so we don't have to worry about it personally too much. But it would be nice to learn how our models for predicting the motion of asteroids due to Yarkovsky effects and such, how we can update these models by actually going to what is one of the most dangerous asteroids. And REX, Regolith Explorer. Regolith is really the dirt on the asteroid, the rocks, the pebbles, the dust. And we're going to map this in very fine detail. So to kind of explain this in a little more detail and having a fun little movie, I'm going to play a little video short.
What is OSIRIS-REx? Does it refer to an ancient god? Is it a space mission? Join the 321 sign.
Do I have to switch back and forth every time?
Science team as we explore just what OSIRIS-REx is. OSIRIS-REx. It's almost all capitals, so it's a good guess to recognize it as an acronym. Scientists and engineers use acronyms to form a word that represents a longer phrase. We say them sometimes as letters or formed into a word. OSIRIS-REx is an acronym that is the name of a NASA mission. This mission will send a robotic spacecraft to an asteroid to return a sample to Earth for study. The OSIRIS-REx spacecraft will launch in 2016, rendezvous at the asteroid Bennu in 2018, sample it, and return the sample to Earth in 2023. The acronym is inspired by the myth of Osiris, and each letter in it tells a piece of the story of the mission. As a whole, the acronym explains why scientists want to go to Bennu and what they hope to learn about the history of the solar system and the early Earth by studying this asteroid. The mission is interested in characteristics of asteroids that can bring life or can end life. The O is for origins. The mission will return a sample of an asteroid essentially unchanged since the early solar system. It's like a time capsule which holds volatiles like water, organic molecules which are needed for life, and other elements which have been isolated for 4.5 billion years. This sample can reveal details about the origins of the solar system and about the building blocks of life on Earth. The SI is for spectral interpretation. Scientists characterize asteroids using telescopes and by studying meteorites, rocks that have fallen to Earth from space. They study how an object's light is reflected from an asteroid surface at different wavelengths and call this a spectrum. They also study how light is emitted from the surface as heat. Comparing asteroid with meteorite spectra allows scientists to interpret what an asteroid is made of, how hot it is, and how big the rocks on its surface are. But to hold a piece of an asteroid and know exactly where it came from will allow scientists to gauge how well they match what they see through telescopes to meteorites and make future matching even more precise. The RI is for resource identification. Asteroids could hold a lot of treasure. Mining asteroids for precious metals and other materials to bring back to Earth promises profit. But perhaps more important are the water and other resources that will allow humans to move out into space. If we really want to explore or even live beyond Earth, we'll need to find resources in space to do that. It's just too expensive to launch everything we'll need from Earth. Identifying what type of resources are available on Bennu will be an important step for future exploration. The S is for security. We know the Earth isn't always a secure place to live. The OSIRIS-REx mission will study the orbit of Bennu to learn more about its potential to strike the Earth in about 200 years. Understanding how the Yarkovsky effect alters the orbit of this asteroid will provide information that can improve our understanding of asteroid orbits in general and lead to better protection from asteroid impacts. REX is for Regolith Explorer. The word regolith is formed from two Greek words meaning blanket and rock. It's the layer of loose material over bedrock on a small planetary body like an asteroid. Exploring the regolith in detail will help us understand composition and processes that occur on asteroid surfaces. OSIRIS-REx will explore the regolith of Bennu at the site where we collect the sample. This will help us place the sample in context and make the sample more scientifically valuable. Over the next 3 years, the OSIRIS-REx team will ready the instruments and spacecraft. Just as OSIRIS was reformed from pieces scattered around Egypt, OSIRIS-REx will grow from components fabricated around the world into a spacecraft that will travel to Bennu to assemble the pieces of the asteroid's story. This small asteroid will help give us a big picture, combining the information about origins, spectra, resources, orbit, and regolith will provide the full story of this asteroid and clues to the stories of many others. This video is an OSIRIS-REx production. OSIRIS-REx is a partnership of the University of Arizona, NASA Goddard Space Flight Center, and Lockheed Martin.
And we actually have a whole series of short videos, about 3-4 minutes, on the OSIRIS-REx mission as well as asteroids in general. We've got a YouTube channel, and it's 321 Science if you want to Google that. We have about at least over a dozen now. I've even narrated one, so they'll get anyone to do it. So a little bit OSIRIS-REx prehistory. How did the University of Arizona end up with $1 billion spacecraft mission? Well, prior to OSIRIS-REx, there was a mission called Hera, which was actually Lockheed Martin, JPL, Jet Propulsion Laboratory, and a science team led by the University of Arkansas. And their plan was to actually go to 3 near-Earth asteroids, recover samples from all 3, and return those samples to Earth. And they had been submitting proposals, I think, through the late 90s and early 2000s. And at some point, either late 2003, early 2004, they kicked Lockheed Martin off. For whatever reason, Lockheed Martin was kicked off the team. So now Lockheed Martin had this asteroid spacecraft concept, an asteroid sample return design concept, but they no longer had a NASA partner and they no longer had a science team. So I believe it was March in 2004, they gave a call to the then director of the Lunar and Planetary Lab, Mike Drake, and basically said, we've got a mission. Would you be willing to serve as PI, or find someone who would serve as PI, and put together a science team? And Mike said, sure, this will be easy. We can do this. So he tagged what at the time was a brand new professor at LPL, Dante Loretta, to be his deputy PI. And with a small Tiger team of about 4 or 5 LPLers, and I was quickly brought on, mainly because I was dating one of Dante's students. That's how the connections work. That's how this stuff works here. Only 3 days earlier, I tried getting into grad school, and Mike had sent me a letter saying my grades were substantially subpar. But then I was invited to be on part of mission. Again, it's funny how all this stuff works. We started working on what at the time was just OSIRIS. So we were going to submit it to the Discovery program. As Shane showed, Dawn was one of the missions for Discovery. I think Dawn is, yeah, as he said, one of the biggest missions at the time, spacecraft. And Discovery is considered relatively cheap. You know, we're talking $400, $500 million missions. Sounds expensive, but if you're going out to other planets and comets and asteroids, it's hard to do that for much cheaper than that. And so we and probably about 24 other teams around the country submitted a proposal. And then NASA got around to selecting the winner of what would have been Discovery 11. And the winner is nobody. They selected nobody. They claimed all our proposals were subpar. Okay, fine. We did learn a lot. Whenever you submit proposals, whether it's for a small grant and especially for something as big as a spacecraft mission, NASA usually tells you what you did right and what you did wrong, what your strengths and weaknesses are. And in fact, you have a conference call with NASA for these big missions where they sit down with you and they tell you, again, what they liked and what they didn't like. And they highlighted a lot of things they didn't like about our proposal. So we knew going forward we had to fix these things. One thing, we were going to try to do this mission without partnering with a NASA field center. No. You got to bring NASA management, at least for NASA, you got to bring NASA management in. They didn't trust our space navigators. So that's where we went and we got kinetics. So we brought the kinetics team on board, the guys in Tempe, and we also brought NASA Goddard on board. So we tried again, 2006, 2007, what would ultimately be the 12th Discovery selection. And this is what the OSIRIS-REx spacecraft looked like back then. If it looks a little familiar, you can basically tell that this was the Mars Odyssey bus. It's got this giant sail on there, which we very quickly realized doesn't really help when you're trying to orbit an asteroid to measure its gravity, and then you've got solar pressure forces constantly pushing on you like a sail, trying to push you over. So we had to change that. But ultimately, we made the finalists. We made the final round of this 2006-2007 opportunity. We were one of three. We were up against GRAIL, which was a lunar gravity mapper, and VESPER, which was a Venus atmospheric science orbiter. And what happens is NASA selects you. Again, you have a debrief where they tell you what you did right, what you did wrong. You take your original proposal. 30 pages are for science. So all your science, why you're going, what is it going to mean for humankind, how are you going to analyze the science and the questions that it will answer, 30 pages. You have basically an infinite number of pages for all the other details. How you're going to build a spacecraft, who's going to build it, what kind of instruments are you going to have, where is it going to be built, what kind of experience do you have, who's going to be on your team, and lots of budgets, schedules, spreadsheets. So these early proposals, we were talking maybe 200-page proposals. So then NASA comes back and says, yay, you win. Here's a little more money. Come back to us in 16 months with a proposal that's 3 times bigger and much more detail. And so you go through all this process again, and eventually you have what in effect is an orals exam, like what a grad student would have. You go in for one day, you've got 50 or 60 NASA reviewers, half of which are there simply for budget, and you have an all-day presentation where you go up there and give 30-minute PowerPoint presentations, and they try to find all the holes they can find in your idea. They loved us, didn't believe our budget, didn't think we could pull off this mission for the $425 million that was the cost cap. So ultimately, we did not win. GRAIL won, which did launch a couple years ago, and their mission's actually already ended. The 2 GRAIL spacecraft impacting the moon, I think, was last year. So the thing we got out of this was that, you know what, maybe we're too big for Discovery. Maybe we need to bump up to the next highest competed planetary mission program, which is New Frontiers. And like I said, the New Horizons Pluto mission and the Juno mission to Jupiter are both New Frontiers. Now you're talking about $800 million for your spacecraft, another $200 million for your rocket, so it's about $1 billion. Unlike Discovery, where as long as you can do it within the $400, $500 million, you can go anywhere. Of course, for that amount of money, you're not really going to get too far out into the outer solar system because of the power requirements. New Frontiers, you're limited to these 8 types of missions. So again, I think there were only 8 submissions. I don't think there was one for every single one. And NASA selected 3 finalists. There was going to be Moonrise, which was going to be a lunar sample return mission from the South Pole Aitken Basin, which, kind of like Vesta, is a large impact basin, again at the South Pole, that goes very deep into the, basically, you run the, well, I shouldn't say you run the risk. The hope is that you actually can sample mantle material from the moon, that you're actually getting deep enough that you're through the crust into the mantle. Of course, we had OSIRIS-REx with our old logo, and then another Venus mission called SAGE, which was going to study the atmosphere as well as have a few landers that were going to make it down to the surface. We won. We got selected. This was May 2011. we found out that we won New Frontiers. The proposal, our final proposal to NASA, the one that we won with, 1,800 pages. 1,000 pages were spreadsheets against budgets, schedules, and if you know anything about budgets and schedules, it's kind of making them up. Because how do you know really what you're going to be doing 8 years out with just a Tiger team? So of course, since then, what have we been mostly working on? Putting together more spreadsheets of budgets and schedules to say this is really what we're going to do and how we're going to do it. So before we start the movie here, which again is another movie which is going to show the mission in action, we're going to launch in September 2016. We have about a 1-month launch window from early September to early October, launching from Florida, Cape Kennedy, on an Atlas V 411, which means we have a single strap-on solid rocket booster. For a year, we're going to orbit in a very Earth-like orbit. In September of 2017, we're actually going to have an Earth flyby, September 23rd, 2017. We're going to use the Earth's gravity then to fling us onto an orbit that matches the orbit of the asteroid Bennu. So after this Earth flyby, we'll then spend another year catching up to the asteroid. And sometime in August of 2018, we hope to get our first pictures of Bennu. And then over the next 2-3 months, we're going to get progressively closer and closer. And then by the end of 2018, we'll actually start orbiting the asteroid. And that's where the movie starts off, kicks off. Volume a little bit. So what we're really going to see here is how we actually collect the sample. So we have the various different instruments basically showing their field of views, and I'm going to go into a little more detail on what each of the instruments are after this movie's over. And that was our laser altimeter. Here's our sample return mechanism. The cover's been jettisoned. And out comes what we call TAGSAM, the touch and go sample acquisition mechanism. We get down to 30 meters from the asteroid and then go into free fall. Thanks to microgravity, we end up only accelerating to a few centimeters per second when we touch the asteroid. Immediately after touching the asteroid, there's some canisters of nitrogen, basically dried air, that we release. It agitates the material on the surface, and then we collect it with the sample return head, which is then put back in the sample return capsule. And again, I've got better pictures and movies later that show this in a little more detail. We leave the asteroid probably around the 2020-2021 timeframe, head back to Earth, and in late September 2023, we release the sample return capsule, which then re-enters and lands in the Utah test range. It'll come down with a parachute, land on the ground, and we pick it up. Very similar to how the samples from Stardust were recovered. The spacecraft itself will do a maneuver where it flies past the Earth and may go on to other things. So the instruments. Of course, we have a camera system. Now, the first 2 times we submitted the OSIRIS, what was at the time just the OSIRIS mission, it really was bare bones. Like Shane said, a low-cost airline. It had a camera and the sample return mechanism, the sample collection mechanism. That was it. We didn't have the money to put any other instruments. Now for OSIRIS-REx, we've got not just 1, but 3 science cameras. And this doesn't include the 3 navigation cameras that we also have. So we have Polycam, which is effectively an 8-inch telescope. I mean, it's kind of it's faster than your typical C8 that you would have, your Celestron C8. We've got MapCam, which will do most of the mapping. Basically it's a wide field of view, so you can frame most of the asteroid in it. And that's a very small refractor. And then SAMCAM really only looks at the actual sample event as it happens. It's only focusing about 5 meters in front of itself, and it'll document the actual sampling. Up in Tempe, ASU is building OTES, which is a thermal emission spectrometer. Very similar to the thermal cameras that they've launched on pretty much every Mars mission seems to have a ASU thermal camera. And they also got a contract to launch one on the New Europa mission. So they'll be the ones measuring the asteroid from 5 micron out to 100 micron, basically measuring the heat radiating off the surface. NASA Goddard is building a visible and near-infrared spectrometer, which goes from 0.4 out to about 4.5 micron, where we expect most of the mineralogical features to be. The Canadians are contributing a laser altimeter called OLA, which basically just like this laser pointer, and it'll have a little scanning mirror. So as we're going over the asteroid, we'll be able to do this, and each point it will be measuring exactly the distance to the asteroid. Not only does that help us figure out exactly how far away from the asteroid we are, but it allows us to build a very fine, high-detailed map of the actual surface of the asteroid. And then REXIS, the only instrument that doesn't start with an O, the Regolith X-ray imaging spectrometer, is actually a student experiment. This is being built by undergraduates at MIT with a few from Harvard. And what it's going to do is, as the surface is fluoresced by basically particles from the sun, you can figure out exactly what the surface is made of. Is it iron? Is it silicon? Is it magnesium? And that's what this instrument's going to do. So we pretty much have our bases covered here, all the way out from, X-ray, gamma ray, and then from 0.4 micron all the way out to 100 micron. In fact, this is out of date because OTES actually extends further than when this was originally made. Being a year out from launch, the spacecraft is being built. And in fact, some of the instruments have already been delivered and have already been installed on the spacecraft. This is TAGSAM. So this is our sample acquisition mechanism. These are actual pictures of what is going to fly, what is going to asteroid Bennu. This is the sample head. This is the head being stowed in basically its protective habitat here for crews. Here's the arm that will extend out. Now, I don't know if anyone kind of recognizes this shape. Does this look like anything familiar? Especially those of us who've been around a little while. Yeah, it's a car air filter. That's exactly what that is. This idea has been bouncing around Lockheed Martin since 1979. And this is how it works. Sample head hits the surface, we release gas, it agitates the surface, throws up the regolith, which then gets caught by the air filter. We will only be touching the surface for about 5 seconds, though most of this agitation and capture of regolith will probably occur in the first fraction of a second. The plan is to bring back 60 grams. Our tests show that it's possible we can bring back as much as 2 kilograms of material. The nice thing about this design, no moving parts. We have canisters. The pyros, we actually just blast them open with pyros. Again, we don't have to worry about anything screwing or unscrewing. And the only moving part really is that it will be gimbaled, so as we land, we won't, we'll have a little bit of leeway to kind of conform with the surface so we don't snap anything off. After we collect the sample, this is where the sample head is stowed. This is the sample return capsule. So this is sample return capsule open. This is with it closed. And then just to kind of show you an idea of the size of the spacecraft bus is here. And this is actually our high gain antenna, how we're going to talk back to Earth. So why are we going to asteroid Bennu? We currently know of the exact number, and I looked it up this morning, is 688,900 asteroids that we currently know about. So how did we end up with Bennu? Well, yeah, there may be 700,000 or so asteroids, but they're scattered all over the solar system. And, we could go into the main belt, like Dawn is, but of course Dawn doesn't have to come back. It would take Dawn just as long to get out there, to come back, as it did to get out there. That would be a really long mission. It would probably push us over our budget. So of the 700,000, you probably want to restrict yourself to objects that come a little closer to the Earth, say near-Earth asteroids. Well, there's about 12,000 near-Earth asteroids. It still sounds like there's a lot of targets. You shouldn't have a problem finding where you're going. But of course, not every near-Earth asteroid is on an orbit that is conducive for sending a spacecraft there and back. A lot of the asteroids are on orbits that are inclined, meaning, if the plane of the solar system, here, we'll do it on here. If the plane of the solar system's here, they're going like this. They're going way above and below the plane of the solar system. It would take a lot of energy, a pretty big rocket, to be able to match the orbit of something like that. Some of them get too close to the sun. Then you have to start worrying about thermal effects on your spacecraft and putting a heat shield. Some get too far away. Now you have to start thinking about gigantic solar panels, maybe even RTGs, radioactive power sources. And if they're in really high eccentricity orbits that go out far from the sun, even if you're able to go to that asteroid and come back to Earth, when you come back and land, you're re-entering the atmosphere at such high velocities now that all of our previous basically it's outside the window of our previous experience. So one of the constraints we had was going to an asteroid where, returning from that asteroid, we wouldn't come back at a higher velocity than the Stardust mission did. The reason for that is you can use the heritage from Stardust. You wouldn't have to develop something brand new, a brand new technique. So when you limit yourself to objects that are in what we call low delta V orbits, those orbits where it doesn't take a lot of energy to get to them or a lot of energy to come back from them, you find that number 12,000 drops now to about 750. Again, sounds like a lot, but there is a little gotcha there. The majority of the objects that are in those low delta V orbits are extremely small. Some of them are as small as this desk. A lot of them the size of this room or this building. There's two complications with really small asteroids, as NASA is learning with their asteroid recovery mission. Small means they're faint. They may have been discovered from Earth, but very quickly, after a few days, they've flown past the Earth, they're now too far away, and we don't see them again. So they're effectively lost. You're not going to find them until they just happen to come close to the Earth again at some point in the future and they get rediscovered. Another big problem is when you get to objects smaller than about 200 meters, they rotate really fast. Most of the asteroids rotate at most once every 2.2 hours. A lot of them rotate more slowly than that. The small ones can rotate extremely rapidly. In fact, our current rotation speed record holder is 16 seconds. How do you land on something that big that's rotating that quickly without also kind of, you can't just settle on top of it and slowly descend. You'd be corkscrewing around with it. Also begs the question, if you're rotating that quickly, how are you even, if you do have material, pebbles, regolith on the surface, what's holding them there? Wouldn't they be thrown off by an object that's rotating that quickly with the gravity being so low? And so you run the risk of going to an object that might just be a monolithic chunk of rock, and there's no regolith to pick up anyway. There's no sample to bring back. That's why for the NASA ARM mission, they basically just said, well, bring back an entire asteroid. We'll pick one that's really small. It's hard to find one that small with a good enough orbit, but pick one really small and just bring the whole thing back and not worry about whether there's regolith, pebbles, whatever on the surface. So once you get rid of the small guys, we're down to 80. 80 objects that we can possibly go to. Of course, we're interested in a particular kind of asteroid. We want to go to a carbonaceous asteroid. We want to go to an asteroid that at some point in the past had a lot of volatiles, perhaps water ice, like Ceres does, and is organic rich, has many of the building blocks of life on Earth. In fact, we think these are the objects that may have brought originally the water and organics to Earth. Well, if you want to go to carbonaceous, you have to know something about the asteroid. You have to have some physical characteristics determined for it. So now we're down to 23 that we know what type of asteroid they are. The majority of these objects haven't been well observed. And if you're interested in carbonaceous, now we're down to 7. Though to be honest, when we first started doing this in 2004, we picked a different asteroid. Based on a single spectrum, we said it's carbonaceous. We'll go there. NASA said, we don't believe your object's necessarily carbonaceous. NASA was right. We got Spitzer measurements of it a few years after the 2004 opportunity, and it had a 30% albedo, a little too bright to have been a carbonaceous asteroid. So ultimately, why did we end up with Bennu? Because of the 7 carbonaceous objects at the time, Bennu was the one that was best characterized. And what really pushed it over the edge is we had radar observations of it, which I will show. And what I mean by radar observations, we have an actual map of the shape of the asteroid down to about 5-meter resolution. So even though we haven't been up close to take a picture of it, we have this nice shape model. And that pushed Bennu over the edge. If we were to do this same exercise today, there would be 2 other asteroids joining Bennu in the list here. 1999 JU3, which is the Japanese Hayabusa 2 mission is going to for their asteroid sample return mission, so they grabbed number 2. And 2008 EV5, which the European sample return mission, Marco Polo R, hasn't been officially selected yet, but they're kind of in and out of running. That's the one they want to go to. So if you do find a nice carbonaceous asteroid that's easy to get to, very quickly people start planning missions to go there. So again, movie time. A little bit about the history of Bennu and how Bennu came to be.
The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
So Bennu, what do we know about its orbit? Thanks to radar observations that we got in 1999, 2005, and 2011, Bennu has actually one of the best characterized orbits of any body in the solar system. We know its semi-major axis, its average distance from the sun, to within 5 meters, which is pretty good. Which means when the spacecraft gets there, and there will be, perturbations and various chaotic stuff that affects the orbit and motions of the asteroid, it should be within about 10 kilometers of where we expect it to be, which is extremely close. It would be very easy to find. As you can see from its orbit, it gets a little closer to the sun than the Earth, about 0.9 AU, so that's 90% the Earth's sun distance. And it gets out to about 1.4 AU, so about 40% further out than the Earth's sun distance. And it crosses the Earth here on September 23rd, which is why we launch in September. It's why our Earth flyby in 2017 is on September 23rd, and why the sample comes back on September 23rd. That just happens to be when the orbit crosses, and we use spacecraft thrusters to sync the motion of the spacecraft so it intersects this point for the Earth flyby as well as returning the sample. This is an actual model of what Bennu looks like. The craters and the very fine detail we just added, those are just kind of artistic license. But the general shape is actually what we believe it looks like based on the radar data. The name Bennu, we had a competition, I think it was about a year or two ago, open to school kids all around the country, submit a name. We got something like 7,000 submissions. And ultimately selected a submission by I think it was a 9-year-old boy from North Carolina, who liked the name Bennu. First of all, it's Egyptian. It's named, there's a stork that's kind of related to the Phoenix, which of course we liked because that little bit of a connection with the Mars Phoenix mission, which was also an LPL mission. But he said the spacecraft looked like a stork when it was descending down to sample the asteroid. So we thought that was pretty good, so we went with Bennu. Plus it was short, sweet, easy to pronounce, even though is it Bennu or Bennu? We have this argument back and forth, what's the ancient Egyptian pronunciation of these things? It's roughly 0.5 kilometer across. It rotates once every 4 hours, 4.3 hours, and it has a density that's a little more dense than water. Now that doesn't mean there's water in it. It doesn't even mean there's ice in it, though that's a possibility. What it probably means is that most of this asteroid is empty space, that the asteroid has basically been shattered, what we call a rubble pile, and there's a lot of little empty voids between the rubble components. So if you were to, so even though the rocks themselves may have a density much higher, when you add what we call the bulk density of the entire body, it's significantly lower because most of it is empty space. Almost like Swiss cheese, even though the analogy only goes so far there. So here were the radar observations. They were taken with, NASA has a radio telescope called Goldstone, which they use for communicating with most of the interplanetary missions, but they also use it to basically ping asteroids. And Arecibo, which is down in Puerto Rico. And it produced their shape model, down to a resolution of about 5 meters. One thing you kind of notice off the bat is no craters, no mountains. There's little bumps. That might be a boulder, 15-meter boulder, maybe. And that's the only boulder we see, even though there's been a lot of asteroids that have a lot more boulders. So one question we always get asked, and one question we really ask ourselves is, so what, we have this radar model. Is this what the asteroid's really going to look like? Because as Shane showed, you know, our pre-dawn views of Ceres and Vesta were a little different than what the object actually looked like. And, you know, we had Pluto. Prior to Pluto, we had HST observations. And we got a very coarse map of very, you know, albedo regions on Pluto. Of course now, thanks to the New Horizons, New Horizons flyby, we've got a much higher resolution. And it looks like the HST models probably were reasonable, potentially, if this corresponds with that, which I just kind of put that there, it may not. But of course, you have all this fine detail that you had no idea was going to be on the surface. Kind of our worst case scenario. The Rosetta spacecraft with the Comet 67P Sheremetyev-Gerasimenko. There was no radar observations of 67P. It's only a couple kilometers across. It doesn't get very close to the Earth. HST can't resolve a nucleus that small. Plus, when the comet is close to the Earth, it's got a giant coma around it. You're not going to be able to pick out the nucleus from all the dust and gas that's around it. So it just looks like a point of light that they observed when it was out at aphelion. And they got a light curve. As it rotates, the object will get brighter and fainter as, you know, the long end or the short end reflects light back at the observer. And say they used a technique that you can use with light curve data to kind of build the shape model. Except usually when you do this, you have to get light curve data at all different observational geometries, and that usually means observing the asteroid or comet all the way around the sun. They didn't have that luxury, so they really took a technique, pushed it probably past its limit. So of course, when we finally got to the comet, it looked nothing like this. It was, you know, it had one big body here, a smaller body here, connected by a neck. It kind of looked like a duck when we were coming in. Not at all what you expected from this shape model. So that, you know, gives us a little pause of concern. Luckily, we do have one asteroid that we do have radar observations of and a shape model, and we do have spacecraft in situ observations of, and that's the asteroid TOUTATIS, which is a near-Earth asteroid. Looks kind of like a peanut. You know, there's two lobes, again connected. The Chinese sent a spacecraft that originally was in orbit around the moon, and after it ended its lunar mission, they had enough fuel that they went out and they flew past this asteroid. And that's what they saw. That's a pretty good match to that. So these radar models do get you in the ballpark. And so we have high confidence that when we get to Bennu, it's going to be fairly spheroidal. And then also the light curve, which again is observations taken from a telescope, as a broader face points to the observer, it gets brighter. As a narrower face, it gets fainter. That also suggests that it's fairly spheroidal. But there is one feature that kind of sticks out, and there kind of is this little equatorial bulge, like it kind of gets a little fat there in the middle. We see this fairly common with asteroids. And in fact, in some asteroids, for asteroids that actually have satellites, this is almost always there, this bulge. What it suggests that an object like Bennu at some point in the past spun up fast enough that it actually shed mass. Material came off the asteroid, which may or may not have formed a satellite, which has since been lost. We know from the radar observations that there's no satellite there now, at least nothing that's larger than a few meters. So it's very possible that it did have satellites in the past, and that satellite either was ejected out into space, and maybe there's a little ex-Bennu flying around, or it crashed back down on the surface. We have Spitzer thermal infrared observations. So we can measure the albedo of Bennu. How much light does it reflect? It has an albedo of 4.5%, which is half as reflective as what Ceres is for dawn. Instead of asphalt, we're talking coal. This is a dark asteroid. The thermal infrared observations also allow us to measure what's called the thermal inertia, the thermal conductivity of the surface. That gives us an inkling of exactly the properties of the surface. Is it bare rock? Is it bedrock? You know, is an asteroid, does the surface not have any soil or regolith on it at all, and it's just a solid chunk of rock? Or is it completely covered in sand? And based on what we have for Bennu, it suggests that it's mostly sand, that the average size of the particle on Bennu is less than a centimeter across. So we're not talking a big rocky object with lots of boulders like Itokawa was, the Hayabusa 1 target is, which is really good for us, because one of your fears when you're trying to land on an asteroid to get a sample is you don't want to run into one of these boulders. You want to have an area like this, which is fairly benign, mostly sandy. And so if most of the asteroids like that, that makes it easy. I mean, we have all these matrices that we've come up with where, you know, we have 58 different scientific values and parameters. We're going to plug into a model, and it's going to tell us the most scientifically interesting part of the asteroid to sample. But when it comes down to it, we're going to go to the safest spot, the spot that's least likely to cause us major headaches. But going back to the real reason for why Bennu, and why not an object that's of a different type, is that we want to go to an object that we believe hasn't changed much over the history of the solar system. That still has, because most of the objects, and this is true of like Vesta, as well as the planets, they got hot, they differentiated, things separated out, things changed. The belief is that for these carbonaceous objects, that wasn't the case, or at least a minimal amount of change. And so the hope is to go to an object that hasn't changed over the solar system, so it really does act as a time capsule, providing us with the material that was there 4.5 or even 4 billion years ago, the stuff that was raining down on the Earth, that was bringing the volatiles that, you know, created the Earth's ocean, as well as bringing the organics of which life itself is made of. And that's why we're trying to bring, you know, samples back, is so we can say for a fact that the samples we have here, unlike the samples that are out there, which are probably contaminated by Earth's atmosphere, Earth water, we have a true sample of what the early solar system was made of. Thank you. And if you want to learn more, and while that's going, you know, wink, wink, nudge, nudge, here's the real reason why we're going. Thanks to YouTube. Much better radar observations than we got with ours. Yeah, questions while we're watching this? So Bennu has a pyramid just like Ceres. And the funny thing is our 15-meter boulder, even before this came out, we kind of informally named Ben, which is the capstone of a pyramid that the Bennu bird would sit on top of, so it all fits in. It's all, the conspiracy is just, everything connects. No questions? There we go.
So if this thing is kind of a rubble pile, if this is a rubble pile, how likely is it that it's pretty loose and that you will have some small stuff in the area orbiting it?
That, in fact, is one of my jobs. As we're approaching the asteroid, one of my key responsibilities is searching for material in orbit around Bennu. Up till now, the other missions have looked for satellites, though the satellites have been pretty large. I think in the case of Ceres or Vesta, that we're talking tens of meters. They looked for satellites tens of meters across. I know the Japanese looked down to 1 meter in size around Itokawa and didn't see anything. We're planning on looking down to 10 centimeters, which is much smaller than anyone else has seen. We don't actually expect to find any material around that, just because the gravity is so low. You really would only expect to find satellites on stable orbits within about 10 kilometers of Bennu. And even when we say stable, we're only talking stable on the course on the order of years. Eventually stuff will be perturbed and either will crash back into the surface of Bennu or be ejected out of the system. At some point, it will cause, it will have another shedding event. It will create a new satellite. Hopefully not hopefully after we get our sample. The act of getting a sample probably will eject material into orbit around Bennu, so it will have satellites after we leave for at least a little bit of time. It's a possibility, but it's a fairly low possibility, but it is something we're going to look for.
Two questions. What's your backup plan if OSIRIS-REx, because I know that there's a long transmission time, so you can't really operate it remotely.
Yep.
What happens if OSIRIS-REx, since you said it was supposed to be composed mainly of rubble, it's called a rubble asteroid. What happens if the grab and go unit is it sort of like what happens if it falls into one of those spaces between the rubble?
So we actually have 3 gas canisters. So we can attempt 3 different sample acquisitions. So if we do drop down, everything works except for some reason we hit a part of the asteroid where there's no sampleable material, we can try it again 2 more times.
That's it.
Oh, okay.
To follow up on that question then, is there enough time and you'll have the camera report back after each sampling?
Well, the problem, of course, with all these missions is that for us, we're 19 light minutes away. So we can't joystick the spacecraft. So effectively, we're going to be in a 1 kilometer orbit. We're going to do a burn where we start descending towards the surface. We do have cameras that will be looking at the asteroid, and we're going to do natural feature tracking, kind of like terrain recognition like we use with our cruise missiles and stuff. So the spacecraft will have a model of the asteroid in its memory. And the spacecraft will know where it should be relative to these features on the asteroid. If everything looks okay, it continues on its glide path down towards the surface. If it looks like something's wrong, then we just basically do a thruster maneuver and we get out of there. So the spacecraft will have enough intelligence, kind of like throwing a dart at the bullseye, at the board, and as it's going, it's looking, am I on target? I'll continue. If I'm not on target, I'll go fly off this way and go throw the dart again at a later date. We will get the data back within hours, but by then what will happen, of course, is we'll thrust away from the asteroid. Whether it's successful or not, we're going to be 50 kilometers away. We'll analyze all the results, figure out whether we got any sample or not. If we didn't, figure out what went wrong, and this will probably take some time, and then determine what's the course of action beforehand. But even before we do this, we're going to have a bunch of test maneuvers. One where we descend down to 250 meters. Another one where we descend down to 50 meters. One where we match the asteroid at 30 meters and we're about to drop, kind of like what Apollo 10 did before Apollo 11, but we ultimately don't. And then we finally make our final descent. And there'll be weeks between each of those tests so we can kind of digest what we learned.
So after the main mission is complete, since there's a bunch of other instruments to use, is there anything else you're going to be doing with the main spacecraft?
Officially, no. But with most spacecraft, if they're still in working order, NASA usually funds what they call an extended mission. So after we pass by the Earth, we're actually going to be flung inbound, basically to the vicinity of Venus. And we could potentially do a Venus flyby that then kicks us out into the main belt. The spacecraft's not really designed for the temperatures that it'll encounter when it gets that close to the sun, so there's a possibility the spacecraft may fail. But if it still works, one of the plans bouncing around in our head is, if we go out into the main belt, maybe we can visit one of the potential parent bodies of Bennu, one of the 4 or 5 large asteroids in the inner main belt that we've identified as possibly being the original parent of basically the daughter Bennu. So it's a possibility. We'll do something. If that spacecraft's still working, someone will do something with it.
So, when the OSIRIS-REx is like flying through space, like what kind of jet propulsion is it using?
We actually have your typical rocket engines, where you have a fuel and an oxidizer, what they call bipropellant rocket engines. So we're having kind of your more traditional rocket propulsion, very different than the Dawn mission, which had the electric ion engine. And to be honest, the reason why we went with the old-fashioned way and not the Dawn way was because when we were doing the 2006-2007 proposal, Dawn was having problems, budget and schedule problems with their engines, so we're like, oh, we're going to stay away from that. So we went with the old-fashioned way. And to be honest, we could use the old-fashioned stuff, and that's all we needed. So it's more of your traditional rocket. Okay.